All right. So today we are going to talk about our lab 3. So our lab is pretty much reflecting what you learned in the lecture. And for this lab, previously it was 2 labs, but I eliminated something and combined them together. So turns out some of the elements that we have in the lab is a little bit further ahead of our lecture. So some of the details that I won't talk about today, but in fact, you will learn some of the techniques regarding how to do your lab or that's related. So I leave some of the materials out from the lecture today because some of the stuff we will actually talk about in a lecture in the next Monday and Tuesday. So, but I wanted to start the lab early, the earliest. So let's start with some part of the lab, which give you some idea of what we are talking about. So, after the midterm, we start talking about the processors. So we are actually talking about how to more efficiently use your processors. So effectively, there are 2 ways that we are going to talk about today. One is that can we use the compiler to generate more efficient code running on top of your processor? And the second part, which is probably going to be the lecture in the next week, is that as a programmer, can we write the code making your processor easier can we write a code that exploit the processor features better? So these are 2 directions this lab will cover. And today I'm going to focus on the first part of the lab, which is more about the compiler optimizations, because as far as I know, compiler is no more the required curriculum in CSE department. Is that true? It used to be. It used to be, right? So that's why we are covering it in the class now. So, but before we start that, right? As I mentioned very beginning in the CSE142 lecture, right? You need to know what kind of Pokemon, what kind of beast that you are dealing with. That would allow you to better know, like, okay, what kind of features is it available? So in this lab, in this class, I'm giving you guys it's not the latest, but almost the latest, because, okay, so Intel right now has 13th generation. The processor you guys are using is effectively this one. So this is a 12th generation Intel processor. So how does that 12th generation Intel processor different from the 13th generation? To be honest, one thing I can tell you is not too different. The only thing that is different is probably the process technology. So you guys are effectively using the latest generation of the Intel processor. And because of the update, so a lot of stuff that we were talking about doesn't actually, so a lot of, like in your lab too, you'll find out that the cache miss rate is surprisingly low. And at this point, I have no idea what's going on yet. But my suggestion, my speculation is that there might be a lot of prefetching optimization that's happening right now, which I will try to try my best to verify that. But at this point, you can imagine you are working on the best processor architecture in the world of x86 for now. And here is the high-level architecture, microarchitecture of that Intel processor. And the detail, you can find this in this paper. And I also give you that link on your lab 3 document. And so if you look at this one, right, in the very beginning, you feel like, what is that? What the heck is that, right? But if you pay attention, you will figure out it's pretty similar to a lot of figures that I show you guys or I draw on the slide, except the fact that it's expanding it, right? And a lot of the terms, if you come down, you'll feel like, I know what is that. For example, you know what is TLB now, you know what is iCache now, right? And what is BPU, branch prediction unit, right? So you already know what is BPU, right? And there is a micro up cache. So for the micro op cache, if you guys has some idea about the history of x86, you will know that well, x86 belongs to some kind of instruction set architecture called x86 CISC instruction set architecture. And then later on with John Hennessy and David Patterson, a lot of people were promoting the idea of RISC, reduced instruction set architecture computer. And the reason is because by reducing the instruction set architecture, you can simplify the design of your processor. And with that simplification, you are allowed to boost your clock speed a little bit and make your pipeline easier, make your processor easier to pipeline. So that's the whole idea. But right now, with x86, they know this. So what they do is that, okay, so we just make the x86 instruction set architecture itself as a front end. But at the back end, they would emit, they will have a lookup table. They will say like, okay, if you see this x86 instruction, how are you going to translate that instruction into a set of this micro ops? So this micro ops is a set of simplified, small and more regular instructions that is easier to pipeline. So although you see like, okay, x86 has an addition, like an addition with memory operations, right? But right now with that, you can imagine that x86 processor itself, this unit, they would decode, when they decode, they would actually make a single very complex x86 instruction into several small ones. So for example, if you have an add that also deal with the memory, what end up would happen is probably that instruction will be decoded and separated into an add instruction, a memory operation, right? And for the add instruction, it probably only deal with the registers. So after you decode those instructions, they will be put into a micro ops queue. And then they will do some kind of scheduling, which we will talk about what this kind of scheduling would do in the next week. And there are many complex algorithms. But now you see a set of ALUs and functional units, which is pretty similar to some of the processor figure that I show you, right? So some of you read the textbook, you might be wondering like, okay, why don't I never talk about the data path in a textbook? Because the data path in the textbook is never like this, right? And this is what you are really in use, right? And also like, okay, this is like the 48 kilobyte DCU, right? Data cache unit, right? So that's data cache, and this is like the 2 megabytes L2 cache, and there's an SOC. We can talk about the SOC in the last week of the class, but this is your processor right now. And here are all the features, right? Like you see, okay, I have multiple ALUs together. I have multiple address generation units. So the AGU here is the address generation unit. It generates the memory address for each memory request. And then once you finish the memory address generation, it will be put into the load store unit. So the load unit, store unit. So that's what your processor looks like. So now the question we are going to answer today is that, okay, with this many features right now, you can have a high level idea. What do we want to use? We have a processor with many instructions that can handle many instructions concurrently. We have a processor that needs to decode its instruction into multiple small instructions, right? So a few things. First of all, we are going to talk about compiler optimization. And the second thing is that how can we generate code or create code that can exploit instruction level parallelism, which means that we are able to run multiple instructions on different hardware concurrently. So let's start with this code snippet. So this is bubble sort, right? The simplest type of sort that you would ever learn as in an algorithm class. And don't judge if this is a good algorithm or not. But the whole purpose of this is that we want to let you know this is we want to use this as an example code. So for these pieces of a code, right, we know there is a swap, and from the class, you know how to implement the swap. So and also there's a branch here. There are two nested loop here, right? So that's the example code that we. And so, but before we start, there's a concept that I want you to know is that when a compiler generates your code, some kind of structure that they need to use to understand the behavior of your code. So the very first type of graph is called control flow graph. There are more. There are also code graph, data flow, but today I'm going to focus on the control flow graph. So you can think about, right, when the compiler tries to analyze your code, they want to know how this, what's the logic flow of the code. And that logic flow turns out to be the control flow. So if you think about what we have talked about in the class in the past, right, the only command or the only instruction that will change the logical flow of your program is actually the branch instructions. So what this control flow block graph does is that we try to figure out. So here's the thing, right? You can imagine your code is pretty much like this. If I have a command, like for example, I have an add, I have a subtraction, I have something like a move, right? All this instruction, all these three, they will be executed sequentially, right? And unless you miss some instruction like J and E, that's the only chances that you will change your direction. So control flow graph is pretty much thinking about, okay, so if these four instructions, they are going to be run together, they should be considered as a single unit of execution, right? So this four, they will be grouped together when we are doing compilation. So they have to pick, and so if they are a single unit, right, no matter how you optimize the code within this, won't affect the execution flow of the rest of the program. Do you agree? So that's why we say compiler optimization is limited, because first, the compiler optimization want to make sure that you don't change the logic flow of your program. So their optimization is pretty much limited in this small scope. So they want to figure out where the small scope is. Yes.
Would we call that atomic?
No, atomic is not, because you can break in every instruction, right? So, but it's considered as an integral unit in execution, right? So if everything goes well, right? So this is essentially like well, it's not atomic because you sometimes has an interrupt, right? But if you don't have an interrupt, right, the whole thing here is essentially like an atomic unit, right? So you want to figure out how many units are like this, right? So it turns out control flow graph is something like this. So if you think about, if you break up the bubble sort code like this, right, you will figure out the control flow graph is pretty much reflecting this execution. So first of all, when I do I equal to 0, right, I equal to 0 itself is a statement, right? So it's not changing. However, afterwards, the very first thing that I need to do is that, okay, once I assign I equal to 0, would I be smaller than n minus 1, right? So that's actually the next statement that I would make. And that's where you are going to see a branch, right? Because if taken or not, there is a branch, right? So that's why you would think of, so here I'm not talking about the real control flow yet. I'm talking about the control flow from the programmer's perspective, right? So you know here, well, for I equal to 0, then I would have go to this one, right? And now, once I'm done this judgment, there would be two cases. One is that I would either return or go to j equal to 0, right? When I go to j equal to 0, then I would probably go to this statement to judge if this is valid. And depending on the result, I would have different ways, different places to go, right? So that's pretty much the idea of control flow graph, right? And now, okay, so But when you compile your code, right? So the compiler basically try to do this kind of analysis to generate a control flow graph. And within a control flow graph, if it's within a base, so here's the thing. As we just said, right? The force right. So this thing itself has many instructions to implement that, right? So for these instructions that are forced through without, so for the very first instruction that is not a branch to the first, okay, so now, okay, so maybe I should say this. So you can consider, right, within this control flow graph, you are pretty much, each of this rectangular is representing a set of instructions in which the very first instruction cannot be a branch instruction until you meet a branch instruction, right? So until you meet a branch instruction, everything should belong to this box, right? So that box is called a basic block in your code. So your code is essentially composed of a set of basic blocks. And whenever you meet a branch, there is a potential of divergence, right? And your code can only go to the beginning of a basic block, right? Because if you think about like, okay, I'm going to this statement, right? You have to go to the beginning of that statement, right? So that's the idea of control flow graph, right? And in this way, you can consider each basic block is pretty much like an atomic unit of execution except for the fact that because we have interrupt, we have exceptions. So you may get out from the basic block anytime. But other than that, it's pretty much like an atomic unit of execution. And because of that, that's the unit of optimization that the compiler can create. So if you want to figure out how the C code becomes an assembly, you can use -s to generate the assembly. However, in our lab, we already created tools for you. So when you run the cells, we will show the control flow graph as well as its assembly language for you. So you don't have to worry about that. But what I'm telling here is that, okay, if you are not using our lab and if you are still interested about if I randomly write some code, how does that work, right? This is what you could do. Okay, so saying that for the bubble sort, I use the compiler to generate these pieces of a code. Very complicated, right? But as you can see, as I just mentioned, right? If we start from the very beginning, so how to read this assembly code? First of all, when you see a dot, don't worry about it. It's pretty much like a comment in some sense. It's for you to read. So, or so like this one, right? It's basically tell you, okay, that's the beginning of a function, right? Because you see like CFI underscore start procedure, right? And here, at the end here, you see an end procedure. So you know that's the beginning of the function and the end of the function, yes.
What is CFI?
I don't know. To be honest, I don't. Right. And then you see push Q, right? C function interface, I guess. Okay. And then you see a push Q. That's the real instruction, right? Now you see a dot here, right? So again, this is not an instruction. It's just a command for you, right? And it tells you, okay, we have this register. It's used for something, right? So this will start with dots. So that's why when you count dynamic instructions or static instructions, this kind of stuff that doesn't count. And the other thing that doesn't count is this. So if you have a column here, it means that's a label. A label is, as I said in a class, it's pretty much like a pointer to an instruction. So if you see a label here, this LBB1_1 is actually pointing to this move L instruction here. And how do I tell where is a basic block? And in fact, pretty much in the assembly code, you can safely say, whenever you see a label until you see a branch instruction. That's a basic block. So you can see like for LBB1 here, right? The instruction is pointing to is effectively not a branch instruction. It's a move instruction. And then move, subtraction, compare. So everything is a non-branch instruction. And now with JGE, that's a branch instruction, right? But when you see JGE, right, the next instruction again, this is a move L. So this is the beginning of another basic block. And then you continuously go and you see JGE, right? So that's another basic block, right? So so if you see what is a basic block, it's basically whenever you see a so like this one, right? This is also a basic block, right? You see, so whenever, so the basic block should start with a non-branch instruction and end with a branch instruction, right? So that's the definition of basic block, right? So you can see like from here to here, you're not going to change your control flow anyway, right? Okay, so that's the code structure. So as you can see, this piece of the code is pretty complicated, and fortunately, we generated a lot of comments because you put a comment, you put a compilation flag code -G here. So that's how we see these comments here. If yes. So that's a good question. So typically we have that case. That's a very good question. So in that case, we should split that into a separate basic block. I guess you see the move instruction here, right? Like, yeah, so this should be considered as two basic blocks, but this is a very complex example. And the reason is because you have different entries. So sometimes when you jump back or jump forward, right, you want to skip some instructions, like for the if else statement, right? There's something that I don't want to do if it's taken, right? Or something I want to do if it's taken, right? That's the case, you will have this kind of block. So I think this should be considered a separate basic block in terms of code optimization, because there are many reasons, but you are right. This should be considered as a separate basic block. Yeah. Okay. So this is the basic structure, right? And as you can see, if you are interested, check those comments, right? That will tell you this is the loop header. This is where the loop, and this is the inner loop, right? And so this kind of stuff, they tell you like this is the depth equal to 2 something, right? So it's they have very detailed comments here if you turn on the -G flag. And if you're interested, definitely you can dig into the detail. So right now, to simplify the discussion, I would just take a look of the inner loop. So the inner loop is the loop that starts with for j equal to 0. So you can see, right, our comments here, we have quite a few, like, okay, so if you look at this one, right, it's subtract 1, right? So you know this is pretty much doing this related stuff. So this is pretty much implementing this guy, right? So that's where this statement is mapped to, right? And then after you're done with this statement, right? So this one, if it's taken, it will go to, if it's taken, it will diverge, right? If it's not taken, then you will go straight forward, right? By not taken, it means that, well, if J is in this smaller, right, then you will go to this one. So for this one, right, you can also see we have a compare. And when we are comparing, right, because this is from array, so that's how you see a lot of move instruction here. They are trying to access the array, right? So you can probably make a guess regarding like, okay, here we are accessing RBP a lot. So you can make a good guess that RBP is probably the base address of the array, right? And then
once you're done with that, right, then again, we have two choices. One is go to the J++, one is go to swap, right? So if you look at the code, right, so you can probably guess, okay, for this one, this is probably the J++, right? And because what you see is that here they are doing like at L1 with EAX, right? And this EAX is probably your J, right? Otherwise, we would just do the swap here, right? But again, after you do the swap, you still have to go back to J++ anyway. So that's why you see both of them in the control flow graph. We go to this one. And what's reflecting here is that although here we jump to this one, but effectively it still go to this one, right? So that's how the code is compiled. And this code is very complex. It has a lot of instructions, right? So, actually I have a lot of comments here. So another thing that we could do is we can turn on compiler optimization. So with compiler optimization, right? The left-hand side is with compiler optimization. Right-hand side is without compiler optimization, right? What can you observe is that, okay, the left-hand side is a lot shorter than the right-hand side, right? And you can see it does a lot of stuff that is that would reduce the amount of instructions. For example, in the right-hand side, you see a lot of move instructions, right? But here they are all gone, right? Because instead of loading and storing every variable in memory, here they try to use registers by using this R13D register, right, to store value. So you don't have to move all the time. And as you guys learn, right, accessing memory is slow. Even though you have cache, sometimes you may miss. That's how they optimize the performance. And the other thing, which is more elegant here, is that if you use register, you can directly do this arithmetics. You don't have to move and then perform the arithmetics as well, right? So that's how you shorten the instructions. And that's a lot of stuff it's doing here, right? And also, they also have some very tricky optimization. So like here, we try to use not L, because if you think about -1, it's effectively like taking 2's complement, right? So they are trying to do 2's complement here with not instruction, right? Which is a very non-intuitive optimization, but the compiler does that. So that's how you see how they intelligently use x86 instructions. And so here's the thing, right? A lot of people would ask you a lot of C programming techniques, tricky C programming questions like bitwise operators. But in fact, right now, a lot of this stuff, the compiler can do it. So you don't actually have to do it manually. So a lot of the tricky C programming techniques, I would say, like this, like takes 2's complement to replace -1. You can forget it now if you are allowed to turn on the compiler optimization, because that's one example that the compiler optimization would do for you, right? And so there are many other examples. If you go through the lab, you will see. But in fact, here are the common optimization that if you turn on the flag -01, the compiler would do. For example, they will try to put variables in registers as long as it's possible. And the benefit is that they would reduce fewer memory accesses. And the other thing is that one of the instructions that -00 won't use, but -01 would use is the load effective address. So this one is actually arithmetic instruction. And what it does is that it generates a memory address. However, if you look at the format of memory address, right? The format of every memory address has something like RAX, RCX4, right? you can actually use this to calculate something, right? So for example, if I want to calculate RAX plus RCX times 4, that's when I can use LEA, right? So this is actually a good way to reduce memory address calculations. And if you do this, you can actually make your memory instruction more effective, right? So thinking about that, right? So we talk about the x86. There's a unit that would translate the memory request into micro ops. So this optimization is a little bit difficult to see, but what I can tell you is that previously we mentioned you have a move instruction, and part of them is memory address, part of them is the register, right? So if you write your move instruction all the time like this one would be recalculated every time. But with LEA, so you can put an LEA and then move something like a register value to a register, right? And if this is already pre-calculated through LEA, and if you can reuse it again and again, right, you can save some instruction here, because this one would actually be split into several ones. But once you see that's the case, that's probably going to be just one move instruction, right? So that would internally help. And the other thing is that, okay, strength reduction. That's a non-observable optimization, but it actually try to use simpler or more intelligent instructions. For example, like if we see we want to do -1, right, which you do a lot in a loop, we will do like not L instead of subtracting, right? So that's one of the cases that you will see, right? And with optimization 2-02, right, you will see that they try to do a lot of optimization like loop invariant code motion, constant propagation. So for example, if we identify that you have a constant in a code, like for example, if you implement I equal to 0 somewhere, then instead of wasting a register to store that I value, I would just put a 0 in a code, right? So that I don't need to waste a register. Instead, I just hard-coded that 0 to instructions to save a register, which is a precious processor resource, right? So that's the constant propagation. And the other thing that -02 would do is function inlining. So function code has its own overhead. For example, you have to store the register somewhere. But right now, with function inlining, the function call will be gone. So that's what that would do. So something that you can see is that when you are doing this -01, right here, you have a function like call swap, right? So here we are calling swap. But if you pay attention to the code that's generated by -02, there's nothing really performing the swap, right? There's no call swap, right? But where's call swap? It's actually these two instructions, because they already embedded this call swap to your code. So these two lines of code plus this branch is actually replacing the original call to the swap function. That's how you further reduce the instruction count, right? Because whenever you need to call, you have to prepare the stack variable. You have to prepare for the arguments that you need for function codes. But right now, if you combine them together into the code, right, this instruction to be eliminated. So with -02, that's what you are going to get, right? And in your lab 3, you will see a lot of this example. So I don't want to get rid of. I don't want to sacrifice too much of your fun. Okay.
I guess I was wondering stuff like Java.
Does
it have similar compiler, or does it even have? I guess
it does have compiler, but its compiler is compiling your code to bytecode.
Yeah, Java.
Right, and the Java bytecode itself is pretty much a stack machine, which you don't have a lot of registers. So a lot of the tricks that you see here is not going to be effective on Java virtual machine. And the other thing is because they don't actually have registers, everything is in memory, right? So that's why Java is so slow, because everything, every variable access would essentially become a memory access.
Partly why I ask is because, learning Java or C++, they teach you, put your constants, at the top, and all caps kind of stuff. But really, isn't that technically slightly slower than just line-coded values?
Say again?
So like, it's common practice for you to put constants, maybe at the top of your code. Wouldn't it be better to not actually use like variable constants, just hard code like actual values?
If you hard code actual values, that will be faster for sure. Yeah, but the reason why they wanted to put constant in front is because it's easier for memory management. So they can know, okay, I have to pre-allocate this memory space when I'm preparing your code, instead of having the runtime memory allocator as well as the garbage collection, right? Because for the constant, right, when you declare it, it will be existing from the beginning of the program until the end of the program, and they would never vanish, right? And so those memory locations, they know I can just directly come from a pool, right? And you don't have to go through garbage collection. You don't have to manipulate a lot, right? So that's why they are faster, because whenever you touch them, they are not going to trigger like reference counters for garbage collection. They are not going to trigger like dynamic memory allocator, which takes some overhead of that, right? So that's probably why they wanted to declare variables as constant. But as I said, right, if you can hard code that value, then that's probably the best practice in terms of performance. Although people who are dealing with software engineering would definitely hate you, right? Okay, so there are a lot of compiler optimization you will play with in this lab. And so the beginning of the lecture, so the first part of the lecture, I'm just going to give you some concept regarding what are the questions that you are going to interface with. And the second part that we want to talk about, actually, we are going to dig into more details in the lecture next week. So if you are only in the lab but not in the lecture, feel free to watch the lectures the next week. So what we are going to talk about later is that, okay, look at this, right? Your microprocessor has 5 ALUs, also 5 address generation units, plus the load store units. How can we use them concurrently, right? How can we use them concurrently? And here are some of the examples that you will see in your lab. So if you look at the first pieces of code, right, you will see, okay, the second statement depending on the output of the first, right? And then this one depend on this one depend on this one depend on this, right? So from your intuition, can this file be executed in parallel? Not really, right? So they don't actually have the chance to be executed in using this 5 ALU concurrently, right? But if you look at the second case, right, this 5, they cannot be used, they cannot be executed concurrently. But can this A plus 1 equal to A and this I plus 1 equal to I be executed concurrently in a separate ALU at the same time? Right, because they don't have any dependency with each other, right? So you see 2 chains of statements, right? So these 2 chains, each of them can be executed pairwisely. Like this can be, like any of them can be executed together with the other instruction from this chain, right? So similarly, like for this pieces of code, you will see like, okay, I have 5, right? So in fact, in your code, if you are able to create this kind of behavior, like, okay, I have multiple streams of data that do not interrupt each other, do not
do not have relationship with each other. That's the best case you can generate code that can run on multiple functional units together. Okay. But so we will have labs questions that have you go through it, but that's pretty much what you will learn. And the other thing, which is about the branch instruction, right? So in a lecture, we have been talking about, okay, the branch instruction is really, we spend a lot of time talking about branch predictions, but one thing that I didn't talk a lot is the performance of branch. So you will see the same demo in a lecture next week, but here I just want to give you some incentive about it. So let me see, array sort. Okay, so you guys must remember this array sort example that I showed you guys before, right? And for this example, here I am enabling my performance counter before I call this calculate sum function, right? So what I'm doing is that, okay, I just show you before and after enabling the sort function, what's the difference in terms of performance counter values that I measured? And here is what we see. So for the same data size, for the same number of iterations, if I have sort disabled, the instruction count is like this. And this is with the sort enabled. The instruction count is also like this, right? So the instruction count is pretty similar. However, if you look at the number of cycles, there's a huge difference. And their CPI is very different, right? And and the answer is that because these two pieces of code, the first piece would make the branch behavior easier to predict. With sorting enabled, you will make your branch easier to predict, right? So with with the sorting enabled, you are only going to see like 3K, around 3Ks of branch misses. But without that enabled, right, you are going to see like 35 millions of branch misses. So, but what I want to show you is that, right, with 35 millions of branch miss predictions, with the number of difference in the cycle time, the number of cycles, right? If you count that, the difference in misses and difference in cycles would pretty much tell you like how many cycles on average you would suffer if you have a branch misprediction. Agree? So here you can see 34 cycles are wasted, right? So it's pretty much more than like an L2 miss or something. So you know, like, yeah, that's why branch prediction is such a big issue, right? Because it's really expensive, right? So here, I just want to give you some brainstorm. So this is actually a final exam question that I gave to my 142 student last quarter. And well, the reason is because the last time when we do the virtual class, I try to spread out everyone into 4 different teams. And if you play this game before, you know where the icons are from. And but the thing is that okay, what we do is that, okay, we try to, okay, so the code is like, okay, I give you uniformly distributed PID, right, from you guys. And then if I see like if I divide it by 8, right? So here's the thing, divided by 8 is actually divided by 8 and then, sorry, mod A, right? So if you want to do mod A, so this is a programming technique, tricky C programming technique. If you want to do mod A efficiently, you can actually do AND 0x7, right? And okay, if it's smaller than 3, then it's team yellow. And if it's 3 and 4, it's blue. And if it's 5 and 6, it's red. Other than that, it's rocket, right? So, you know, for this pieces of code, we have a lot of branches, right? So how can you eliminate all the branches? Do you guys have any idea? So some of you asked, is there a difference between plus plus I and I plus plus? And the answer is probably no. How can you eliminate all the branches? What's the alternative way of implementing this without generating a branch instruction? No? Oh, you're here for fun? Yeah, for assembly, well, yeah, like, okay. If you put this code, right, and with compiler, it will generate a lot of branches, right? But how can I write this code in a way that it won't generate any branch? What? So if you have an if else statement, yes, the answer is that, right?
Like all the students remembers want to use the first class. And like
So you say you sort them in this way, but there is another overhead, right? And right now, what if I already sort all the students based on their PIDs?
then in that case, I mean, not that PIDs, but
More specific, how are you going to do it?
like pointers by age,
Sort them based on their remainder, but you still have to sort, right? Mm-hmm. Okay. Okay, you guys got it, right? So here's the thing, right? You can actually do this, right? You can create a small table, right? So this is like, okay, 0, 1, 2, 3, 4, 5, 6, 7, right? And this is probably like yellow, this is probably like blue, right? Something like this, right? Okay, so here's the trick. Under what situation this technique won't work? What? Will not work. Like, okay, in modern processor, why it works? Register, but what if I have, well, for this table, do you think we can put everything in a register given the usage we have in a register? Probably not, right? So you have to store them where? Memory, okay. So if our memory is 100 cycles slow, do you think, and considering the branch prediction miss penalty is 34, right? If your memory is slow, this won't work, right? So that's why I'm saying, right? This overhead is larger than your L2, right? Which means it's smaller than L. So here's the thing: if your lookup table cannot fit in L1 or L2, it won't work, right? So if today, what you end up with is a joint lookup table, it probably doesn't worth it, right? But if today you can have your lookup table as small like this one, right? So for this case, an 8-entry lookup table is definitely going to work, right? And it's only 8 times 8, right? It's only like 64 bytes, which is just like a block in your cache. So definitely fit in L1, right? So this technique would work. And then you can avoid the potential of branch misprediction, which is 34, right? But accessing L1 cache is probably 4 cycles, right? So you save 30 cycles in this way. So that's why this is probably a viable technique, right? And in fact, you are going to see similar technique would play out in your programming assignment. So the programming assignment for this lab is actually
Not sure how many of you still know this guy. I know right now we are in the era of LCD, right? So, like this time, like during these days, like even people don't remember what a CD looks like, right? So I'm very cautious and hopefully you guys still know this guy. Oh, okay, lovely. Right, because I still see these guys on my microwave, so I'm assuming it's still in use, right? So you guys know 7-segment display. But in fact, like if you took 140, you already know that, okay, with this 7-segment display, it's actually 7-segment, right? So you have to remap your binary into a so each digit in decimal has to be remapped to like a signal that maps to a segment on this display, right? So here's the mapping table, right? So yeah, you hear the mapping table, right? So the original code that we give you has a lot of case statement, right? And whenever you see a case, we are going to create some kind of branch instructions, right? But look at this table. Remember what I just mentioned, right? This is probably what you can do. Okay, so that's pretty much it. And that's pretty much about our lecture today. And a few announcements. So our tutors, they are very nice. So they feel like, okay, the first lab grading is probably too harsh. So they are pulling it back and they are revisiting everyone's assignment now. So if you don't see your grade right now, it's probably because they are regrading. Also, one thing I do want to make sure that you guys know is that this is a lab. So it's a measurement based, right? So sometimes if your number is a little bit off your expectation, don't worry about that too much. We are worried more if your calculation is based on your measurement. And for lab 2, we have the performance as part of the MEM grading criteria. And the performance is based on the grade scope. And the lab machines are only for you for code development and as a reference design. And one thing I do want to apologize is that because I upgraded the machine for a good purpose because I think I'm giving you the best hardware. But in fact, that best hardware is so good in a way that it lifted up the performance of baseline. So that's why I'm saying, like, if you get 3 times speed up on the lab machine, you are probably going to satisfy in the grade scope. However, that's 3 times speed up is based on the measurement that I use for my standard solution. But code optimization, you can do whatever you want, and I cannot predict what you are going to do. So a lot of cases, you will measure something that is different. Now, that's also 3 times speed up, but that's probably not going to be 8 times speed up on the grade scope, right? So again, the performance is based on the grade scope, not the lab machines that we are giving. So once you're done with the development, once you're passing all the auto grader, you have to go through the grade scope. So that's why we want you to start earlier, because the grade scope server would become busier towards the deadline. Lab 3, which is the one we just talked about, we have a total of 24 questions. So that's a long one. Previous one, I think we only have 17 or something, right? So we have 7 more. All right, so start earlier. All right, other questions? Okay, all right, I will see you next week.